Okay, we are continuing to talk about the fundamental theorem of calculus, aka the FTC, sometimes called. This is the first fundamental theorem, and there's two ways that we could write this fundamental theorem of calculus. Okay, so we could write it as the integral from the left-hand endpoint to the right-hand endpoint of some function dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay, this is one way to write it if you have, or if you know a function, if you know what the function is that we are integrating, and you are finding the antiderivative of. Or we could write it as the integral from the left-hand endpoint to the right, for a to b, of some derivative of a function is the function itself evaluated at the endpoints. Right, so f of b minus f of a. Right, either way, this is the antiderivative of your integral function, or f is, of course, the antiderivative of f prime. Okay, so there's two ways that we can write it depending on how you see your problem. So using the fundamental theorem requires us to take an antiderivative. So if we're evaluating the integral from -1 to 2 of 2x minus x squared dx, the antiderivative of 2x is 2 times x to the second power over 2, because we add 1 to the power existing, so 1 plus 1 is 2, minus x to the third power, because once again we add 1 to your existing power and divide by that power. Okay, so we can do a little bit of simplifying here by 2 divided by 2 is just 1x squared minus x cubed divided by 3. And sometimes you might see it with this crazy calculus notation. You draw a vertical line and we say we're going to evaluate this from -1 to 2. Okay, that's the way AP Calculus knows that you are evaluating these functions, and all you really have to do is put the answer out here. But since my brain doesn't work like that, I'm going to have to do some work. So I need to evaluate at f of 2, which is 2 squared minus 2 cubed over 3. 2 squared is 4 minus 8 thirds. Okay, now here's a problem. I have a number minus a fraction. So I'm going to change my number into a fraction of 12 thirds, because 12 divided by 3 is 4, but now I have the same denominator and I get 12 minus 8, is rather 4 thirds. And now we're going to evaluate f at -1, which is -1 squared minus -1 cubed over 3. So -1 squared is +1. This is a -1 on top times a negative is plus 1/3. 1 plus 1/3 is 4 thirds. So if we go back into do our f of b minus f of a, that's 4 thirds from here minus 4 thirds from here, gives me a total area under my curve of 0. So it looks like the way this works that you have the same amount above the x-axis as you have below the x-axis, which means you have a total area of 0. Okay, let's drop down, because this one is more mathematically interesting, and let's integrate from 1 to 4 this rational function. Okay, we don't want to leave it as a rational. We want to make it into a polynomial. So I'm going to do some exponential subtraction. So this is 2x to the 1 minus 2 power. Okay, when you take and do your subtraction of exponents, when you divide like bases, you subtract. And then, of course, it's just going to become negative there. So I'm actually going to integrate the polynomial 2x to the -1 plus 3x to the -2 dx. Okay, so that is what our rational simplifies to as a polynomial. right, with negative powers. And this can help me because now I can use my polynomial rule, where I add 1 to the exponent, which is 0 over 0, plus add 1 to my exponent, 3x to the minus 1 over minus 1. Okay, so in the video from yesterday, we talked about this business of having an x to the 0. Right? And we decided that rather than differentiating 2x to the minus 1, we would differentiate 2 over x, or rather anti-differentiate 2 over x. Okay, and that turns out to be a natural log anti-differentiation. So whenever we are anti-differentiating an x to the minus 1 and we get x to the 0, okay, that is one of the strange things that we need to know to change to be a natural log antiderivative.
So whatever the coefficient is, just that, like natural log?
Whatever the coefficient is in your numerator is the coefficient of your natural log. Okay, and then minus 3 over x. Okay, and this is what we're going to evaluate from 1 to 4. Okay, so you need to be able to recognize this x to the 0 business as not being a normal antiderivative. It is a natural log antiderivative. Okay, so let's evaluate this at 4. 2 natural logs of 4 minus 3/4. Minus, let's evaluate it at 1. 2 natural logs of 1 minus 3 over 1. Okay? Now, without a calculator, we're not going to be able to write this in a mathematically satisfying way, but we can combine all of the like terms that we have here, which are negative 3/4 and positive 3. Okay, when I distribute my negative, a negative times a negative is a positive. Okay, so no, it's not going to be very mathematically satisfying to have 2 natural logs of 4 minus 2 natural logs of 1. But without a calculator, we're not able to decimalize that unless you have an amazing brain, which maybe you do, and you're able to make that into a decimal in your brains. And then we're going to add 2 and 1/4 at the end, because that's what negative 3/4 plus 3 is going to be. Okay, let's scroll right and look at this trig one. So we have the integral from 0 to pi of 2x plus cosine x. Okay, so the derivative of 2x is 2x to the second power divided by 2, right? Because we have to add 1 to our power, which simplifies to just x squared. Now, what is the antiderivative of cosine? That is just regular sine. Because the derivative of sine is cosine, the antiderivative of cosine is sine, and we're going to evaluate that from 0 to pi. Okay, so let's evaluate it at pi. That would be pi squared plus the sine of pi, minus, evaluating at 0, 0 squared plus the sine of 0. Okay, so let's see. If I go to my unit circle, the sine of pi is 0, and 0 squared is just 0, and the sine of 0 is also 0. So pi plus 0 minus 0 plus 0 is just pi squared. Okay, so it's decent practice to be able to take an antiderivative and apply that to the law of the fundamental theorem of calculus. Okay, remember we're trying to find the area underneath the curve, between the curve and the x-axis. That is what the antiderivative is asking us to do. Okay, so let's look at some problems that you give us to us in another form and to help us with a table. Let me take a picture of that. I'll be right back. So here we have a table and some other integrals. Okay, so if we're going to find the value of this first integral, we have to first anti-differentiate. Okay, and we're going to use the fundamental theorem, which says if we're taking the integral of a first derivative, the answer is found by just doing f of b minus f of a. right? Evaluating the function at the top endpoints and subtracting the value at the bottom endpoint. F of b minus f of a. So for our problem, that is f of 1 minus f of negative 3. And since we don't have a function, we have a table, we're going to look at the table and see what those values are. So let's see, what is f of 1?
It is
Negative 2. And what is f of negative 3? F of negative 3 is 4.
That's 4.
okay. Wait, can you?
So we have negative 2
Oh, yeah.
minus 4, which is negative 6. Alrighty, let's look at the second one. Here we have the integral of negative 1 to 3 of f prime plus f double prime. Okay, so what is the derivative of f prime? Well, that's just f, right? The derivative of f prime, the antiderivative of f prime is f, plus what is the antiderivative of f double prime? Well, that's f single prime. And we're going to evaluate this at negative 1 and 3.
Wait.
Okay, so we're going to do f of 3 plus f prime of 3, right? That's evaluating at our right endpoint, minus f of negative 1 plus f prime at negative 1. Okay, and all these values are going to come from our table. Okay, so we're replacing x with 3 in both of our two functions, and then we're replacing f with negative 1 in both of our functions. So let's go to our table and see if we can find out what we're using here. So f of 3 is positive 1. F prime at 3 is positive 3. So that's 1 plus 3, which is 4. Sorry, I'm writing all over the place. 4 is your evaluating at positive 3 minus f of negative 1. So at negative 1, y is 0, plus f prime at negative 1, which is 1. So 0 plus 1 is 1. 4 minus 1 is 3. So the answer to this one is going to be 3. Okay, number 3. This is kind of going to apply some of the properties of our antiderivative, sort of a little bit. But we have the integral of 3f double primes. So the antiderivative is going to be 3f primes. 3 times f prime evaluated at 5 and 1. Okay, so once again, let's go to our table and find 3f prime of 5 minus 3f prime at 1. Okay, so at 5, f prime is 2. So 3 times 2 minus f prime at 1 is 0. So 3 times 2 minus 3 times 0 is just 6. Okay, so we use the table of values and our antiderivative, and then we evaluate it at your two endpoints. Okay, so that's pretty good. Here's one last example if you want to do it. Okay, we can take the antiderivative once again and get 1/2 of f plus 2 f primes and evaluate them at negative 3 and positive 3. Using our table, this is how you would come up with the answer for this one. Okay, but let's go ahead and skip that so we can get to the interesting part. What is the equation of the tangent line to the graph at x equals 3? Okay, now we went over this in Unit 1, and we need to know two things in order to write the equation of a tangent line.
Oh,
We need to know the points, the x and the y coordinate, and we need to know the slope. So when my x value is 3, what from the table is my f of 3? What is my y value when x is 3?
1.
And if we look up here, we see the y value is 1. Okay, so we have the coordinate point 3, comma 1. And what is the slope? What is f prime at 3? Right, that's how we find the slope. The slope is the first derivative. So f prime at 3, come here, table. F prime at 3 is?
3.
Positive 3, right here. Sorry, just colored it up. F prime at 3 is 3. So now we're going to write our equation in point slope form. Y minus 1 equals our slope of 3, x minus 3, the x coordinate of your points. Okay, so let me change this real quick so I can tell you. This slope is 3, and the slope goes here. Okay, two of the same numbers. So that is the equation of our tangent line. We use the x value to find the y from our table, and then we use the slope from our table also. So we did this in Unit 1 also. Use the equation to approximate the value of 3.1. Okay, to approximate the value of 3.1. So f of 3.1 is approximately, right? Y minus 1 equals 3 times, this is where your 3.1 goes, in for the x value, and we solve this equation for y. So y minus 1 equals 3 times 0.1. When you do 3.1 minus 3, y minus 1 equals 0.3. So y is equal to 1.3. Okay, so if we go back to our original question, f of 3.1 is approximately 1.3. Okay, that's the approximation using our tangent line. Okay, so then, is this an over or an underestimate? Okay, an over or an underestimate. Now, there were two ways that we determined that back in Unit 1. If our graph was concave down, then your tangent line approximation was always going to be above your graph. And we would have an over approximation if your graph were concave down. Now, if your graph were concave up, your tangent line approximation would always be underneath your graph. And you would have an under approximation. Literally, the y value is under what it's supposed to be. So the question is, how do we determine if it's concave down or concave up? And the answer is we look at the second derivative. The second derivative tells us whether our graph is concave up, if it's positive, or concave down, if our second derivative is negative. So what is the second derivative of 3? Because that's our x value. Right, our x value is 3. So what is the second derivative at 3? It is negative 3. So our second derivative is negative. Second derivative is negative, so our graph is concave down. And if our graph is concave down, then the approximation is an over approximation. Okay, that's how we justify your answer. Because we have a negative second derivative, the graph is concave down at x equals 3, and your approximation is an over approximation. Okay, so hopefully that helps us when we're talking about taking the antiderivative and using the fundamental theorem of calculus in both of its forms.